Welcome to Math 275, spring of 2020, and today's lecture on separable differential equations. Separable differential equations, as we all could tell by the name, are differential equations that could be rewritten in a differential form where the variables could be separated and integration could be done separately on both sides, hence achieving an easy solution. So the main objective in a separable differential equation topic would be for you guys to try to separate variables, put all the x's on one side and all the y's on the other side, and integrate both sides, which at that point obviously the issue becomes integration. A separable differential equation could be written such as dy dx is equal to f of x and g of y. If a differential equation could be written in that form, then we could very easily separate variables by writing this as dy equals f of x g of y dx. Keep the f of x that matches its differential and take g of y and take it to the other side by dividing both sides by g of y. This gives me 1 over g of y dy will be equal to f of x dx. And since you want to not have a 1 over function here, just at least for the looks of it, so it looks more comfortable to you, you could just change that to h of y dy equals f of x dx. And at this point, you clearly could integrate both sides and hence achieve a solution and solve for y of x. I'm going to give you some examples because the best way to see it would actually be to look at an example done. So I'm going to start with giving you the following example. So I'll have x plus 1 dy minus y dx equals 0. I'm trying to figure out if this is a separable differential equation, that's what you do on your checklist of going through a problem and looking to see which method solves it, given that you'll be learning a few other methods as well. So if I look at this and I write x plus 1 dy and take y dx and add it to both sides, hence moving it to the other side, I can at this point clearly see that I can divide both sides by y and both sides also by x plus 1 and separate variables at that point. So I could simply write this as 1 over y dy equals 1 over x plus 1 dx. And at this point, this becomes a simple integration problem. The integral of 1 over y dy becomes natural log of y. And you can save the constant and write it on the other side because you're going to end up having to deal with just one constant anyways. And on this side, you'd have the natural log of x plus 1, and then you could write it plus a constant. Now, this could be looked at as the general solution to the given differential equation, but it is customary to write the solution usually in an explicit form if possible, and I get a feeling that it may be possible here to write the solution in an explicit form, so it wouldn't be a bad idea to spend some time on this and use some algebra to see if I could solve for y. Now if I look at this, I have two terms that are logarithmic and one term that isn't, which is a constant, and since a constant could be written as the natural log of some other constant, which again itself will be a constant, I could always replace c with ln of c, which is a common thing to do in this topic. So don't panic about that. So I could simply write this as ln of x plus 1 plus ln of c. And now since I have two ln's that are being added together, I could use the properties of ln and I could write this as c times x plus 1. And now I've combined my both natural logs. Now I know from algebra that if natural log of a is equal to natural log of b, then a must equal b. Therefore, I could simply say y must equal cx plus 1. And I could simply just drop the absolute values at this point and say that's my solution. So there's an example showing you how to separate variables and solve for the fundamental solution. I'm going to give you one more example, and hopefully you'll be on your way in solving all the rest of them after this. The second example I want to look at would be dy dx equals xy plus 3x minus y minus 3 divided by xy minus 2x plus 4y minus 8. Now again, this feels like it's a separable differential equation because when I'm looking at the right-hand side, I can clearly see the factoring possibilities there. So I'm going to pursue that and see if that'll take me to where I could completely separate x's and y's. So I'll start with doing some factoring here. I'll pull out an x, y plus 3, factor out a minus 1, y plus 3. From the denominator, I'm going to factor out an x, y minus 2. And from the other two, I'll factor out a 4, which will give me y minus 2. This allows me to factor further. This gives, if I factor out a y plus 3, I end up with x minus 1. And if I factor out a y minus 2, I end up with x plus 4. And you can clearly see at this point that variables could very easily be separated. So I'm going to write this as x plus 4 times y minus 2 dy, writing this in a differential form, y plus 3 times x minus 1 dx. So now I've converted the derivative form into a differential form. Just want to make a note of it so you guys all realize I haven't crossed multiply. So now I need to separate x's from y's. I'm going to keep y minus 2 dy here. And I'm going to keep x plus 1 dx on that side. I'm going to divide both sides by y plus 3. And I'm going to divide both sides by x plus 4. Now I can clearly see I have two separated sides. One is completely in terms of y, and the other one is completely in terms of x. So at this point, the problem becomes I just need to integrate both sides so that I can ultimately solve for what I want to solve, which is y of x. Let's not forget about that. Now, the question becomes, how am I going to integrate these two quantities? Well, there could be a couple of ways in doing it, but I would think at this point long division would be the way to go. So I'll take, and I'm doing this step by step for you guys so you can actually see it at this point in class. I just told you it's on you to do the long division on this, but you have to separate this somehow so you can integrate it easier. So long division is obviously the way to go. So I'm going to write that as y plus 3, 1, y plus 3. I'm going to change the signs. And you're going to end up with minus 5 as a remainder. So the integral of y minus 2 over y plus 3 dy turns into the integral of 1 minus 5 over y plus 3 dy. So there, I just cleaned up my first integral. Now at the same time, I will do the same thing to the other side. X minus 1 divided by x plus 4. It's a 1, x plus 4, change the signs, you get minus 5 again. So the integral of x minus 1 over x plus 4 dx now turns into the integral of 1 minus 5 over x plus 4 dx. So now I can write both sides of this differential equation that I separated, such as this. And now it's quite simple to integrate both sides. The left-hand side becomes the integral of dy minus 5 integral of dy over y plus 3. And the integral on the right side becomes the integral of dx minus 5 integral of dx over x plus 4. Integral of dy is y minus 5 natural log of y plus 3 equals x minus 5 natural log of x plus 4. So again, this could be looked at as a general solution to the differential equation, because for all practical purposes you have found the solution. And of course, I'm sorry, I have to not forget to, and thank God I'm using an iPad so I could delete stuff. I need to not forget about the constant. So good thing I caught that earlier, which is usually forgotten. So that becomes my solution. And again, at this point, the question is there any way I could make this, use algebra to somehow solve this explicitly in terms of y? But I'm going to leave that up to you to decide and play with. This concludes our lecture on separation of variables, and the next one will be dealing with exact differential equations. See you guys then.